So here you see a brief overview of all the tests that we have to establish convergence or divergence for series. I'm going to briefly review all of them. First of all, we have tests for divergence. This you should always check in your mind if this test applies or not before jumping to any of the other tests. So what does it say? It says that if the limit of an is different than 0, then the series of an is divergent. And limit being non-zero could either mean that the limit is a finite number that's non-zero, that it's infinity, or that the limit doesn't exist. If the limit turns out to be 0, then the test is inconclusive, so you have to use another one. The examples that I'm giving you are series of arctangent of n, and we know that the limit of arctangent as n approaches infinity is pi over 2, and also I'm giving you a series of minus 1 to the n times n over n plus 1. Well, in this case, this is divergent because the limit of the sequence doesn't exist. Why? Because n over n plus 1 approaches 1 as n goes to infinity, and multiplied by this negative 1 to the n makes it switch and oscillate between negative 1 and 1. A rigorous argument would require subsequences, but this is enough for us here. So since there's not a unique limit and this sequence keeps oscillating, then the limit doesn't exist. In particular, it's not 0. Therefore, the series is divergent by the test for divergence. Okay, next, what happens if this test doesn't work? So if the limit is 0, then we have to use one of these other tests. So first of all, we have the comparison tests. These apply to series with positive terms. So you're given a series of an and you're trying to compare to a series of bn. If an is smaller than bn and the series of bn is convergent, then the series of an, being smaller than something convergent, is going to be convergent also. While if the an is greater than bn and the series of bn is divergent, then series of an being greater than something divergent is going to be divergent. In any other case, you cannot conclude anything. If something is smaller than a divergent series, then you cannot conclude anything because everything is smaller than something divergent. Could either be finite or not finite. What about the limit comparison test? Well, that requires you to compute the limit of an over bn. If that turns out to be a number that's non-zero and not infinity, so in the open interval, then series of an and series of bn have the same behavior. Meaning series of an converges if and only if series of bn converges, and series of an diverges if and only if series of bn diverges. Now, when do we want to use the comparison test? Usually, my suggestion is if you have ratios of polynomials or ratios of powers, more in general, then you want to try to compare to the p series. These are series of the form 1 over n to the p, which we know to be convergent for p greater than 1, while divergent for p less than or equal to 1. So here I'm giving you these two examples. You see a ratio of polynomials and here a ratio of polynomials and powers. So by powers I mean roots n to a number, basically. So what you want to do in your head is to just disregard all the lowest order terms. So for example here, we just keep n cubed divided by n to the fifth, which simplifies to 1 over n squared. So that one is going to be compared to the series of 1 over n squared. And same you can do for the other one. This one you can compare to the series of 1 over square root of n, because here we have square root of n divided by n, and that simplifies to 1 over square root of n. So this is going to be your bn, and then you're going to do the comparison with those. If it's easy for you to figure out an inequality, then you can try and use the direct comparison. Otherwise, once you figure this out, then you can just do the limit comparison test. And if you did this preliminary analysis in the right way, then this will always produce a number that's not 0 or not infinity. So it will work. So in conclusion, you would find that this series is convergent and that this series is divergent. Next, we have the ratio test. So this requires you to compute the limit of the ratio, an plus 1, so it's the next term divided by an. And if that turns out to be greater than 1, then the series is divergent. If it's smaller than 1, then the series is convergent. If it's equal to 1, then the test is inconclusive, meaning we cannot apply it. So my suggestion is to use this test whenever you see some exponentials or factorials. And my examples are this one, where you have 3 to the n, which is an exponential, and this one, which has an n factorial. We want to use the ratio test because exponentials and factorial simplify once you have this ratio. The next term divided by the previous term simplified. Then we have root test, which is in the same spirit. This is less used, but you will compute the limit of the nth root of an, and then according to whether this is less than, greater than, or equal to 1, you will have convergence, divergence, or nothing. So when to use it, I don't know. There's not something as easy as this that I can say, but what I could say is that you need to have an expression that simplifies when you take the nth root of that. So here I'm saying if you have some power of n, like in this example, you have some expression raised to n squared. So when you take the nth root, that's going to simplify the n squared, and you're going to be able to compute the limit, which would be hard to do otherwise. But anyways, so here I'm writing that these tests are for series with positive terms. There's also analogous versions. If the series do not have positive terms, then you can put absolute values here, and you will get the same conclusions, because this in particular for convergence, for example, will tell you that the series is absolutely convergent, which implies convergence. But in general, what happens if you have a series of the form -1 to the n times bn? These are called alternating series because the terms are alternating between positive and negative. So the test says the following, that if bn is decreasing and as limit 0, then the series is convergent. So when to use it? Clearly when you spot the alternating series, which is just, it gives it away with that -1 to the n. Could also be -1 to n plus 1 or to n minus 1, that doesn't really matter. And so my example is this, and bn would be n squared over n cubed plus 1, which clearly goes to 0 because the power of the denominator is greater than the power of the numerator. And you can also check that it's decreasing. So this is going to be convergent. Just pay attention, this one over here is also alternating, with bn being n over n plus 1. So in that case, bn does not approach 0. That means we cannot apply this test, and this test doesn't tell us if the series is divergent. But in this case, as we already mentioned, we can use the test for divergence, because if this bn does not approach 0, then when you multiply it by -1 to the n, it's going to oscillate, so it's not going to have a limit. And therefore, the series is going to be divergent by the test for divergence. Finally, we have the integral test. This, you will see your an as f of n, and if your function is continuous, decreasing and positive, then what you can do is compute the improper integral, and then if this is convergent, then your series is going to be divergent, is going to be convergent, and if this is divergent, then the series is going to be divergent. So here I'm saying they have the same behavior. When do you want to use this test? I'd say it's not used that often, but you can use it whenever you see an expression that it's easy to integrate, or if you run out of options and you cannot use any of the other tests. So in my example, I'm giving you a series of 1 over n times logarithm cubed of n, and we can see that if you do a substitution, u equals logarithm of n, this is going to be easy to integrate. So you want to go for integral test. Yeah. By the way to prove this result of the p-series is done through the integral test.